Our next lesson here is working with formulas. Mostly we'll still be doing linear type things, but the real issue here is making sure you know how to manipulate formulas and how to use them to solve problems. A big part of that is knowing what the variables represent. For example, this equation says E equals 0.177t plus 71.35. Now what T represents is the years after 1950. So T is a time, and it represents the years after 1950. And then E is the life expectancy, and this is actually life expectancy for women. So the question that's asked after you're given that information is, when will the life expectancy be 82 years? This is why it's very important to make sure you pay attention to what variable is what. It says the life expectancy will be 82 years. Okay, so 82 years is life expectancy, which means we need to plug 82 in for E. Now we can simply solve for T, just like we were doing in a previous lesson. So subtract 71.35 from both sides. That gives us 10.65 equals 0.177t. Now we divide both sides by 0.177. And you get just over 60. So if t equals 60.169, that means it's over 60 years after 1950, so we would expect it in the year 2010. Next up, we have this equation. It says W equals 0.3x plus 46.6. And this is the average number of hours worked by Americans per week. And this is X years after 1950. Actually, this one's supposed to be 1980. Let me correct that. 1980. Okay? So W is the number of hours worked per week on average, and X is the number of years after 1980. So the question is, when will the average number of hours worked be 55? So again, they're asking a when question, so they're wanting us to find years, they're wanting us to find X, and they give us 55, which is the number of hours worked, to put in for W. So I will put 55 in for W, and then solve for X. Subtract 46.6 from both sides. We get 8.4 equals 0.3x. Divide both sides by 0.3. And we get 28 equals x. Now keep in mind, x is the number of years after 1980. So we have to take 1980 and add 28 to get our answer of 2008. So we would expect, based on this model, that the number of hours worked will be 55 in 2008. Okay, now in these next couple of problems, we're going to have to set up the equations in order to solve these problems. It says the number of cats in the U.S. exceeds the number of dogs by 7.5 million. So let's just stop right there and try to write that as an equation. So we'll obviously say C is our number of cats. We'll say in millions, so we can deal with smaller numbers. And D is our number of dogs in millions. So based on that first sentence, it says the number of cats in the U.S. exceeds the number of dogs by 7.5 million. So the number of cats, C, is, anytime you have is, it's equals to. So the number of cats exceeds, or is, 7.5 bigger than the number of dogs. So that would be the dogs plus 7.5. Or you could say 7.5 plus D. That would be fine too. Since you're adding, it doesn't make any difference. But that's what that equation would look like. The number of cats exceeds, or is, 7.5 million more than the number of dogs. Okay, so that gives us an equation to represent that first line. Now the next line, next sentence says the total number of dogs and cats combined is 114.7 million. So if we add the cats and the dogs together, that total is 114.7. Now the question is, determine the number of cats and dogs in the U.S. In other words, solve for C and D. We have two equations here, and hopefully the hardest part is just making sure you know how to write those equations correctly. But we need to solve for C and D. Well, since this is already solved for C, I'm going to plug that in right here and replace this C with D plus 7.5. So just to be very clear, I'm replacing this C with D plus 7.5. I'm substituting. Okay, so now I can combine like terms. I have a D plus D, that's 2D. I can subtract 7.5 from both sides. That's going to give me 2D equals 107.2. Then I can divide both sides by 2. That's going to give me D equals 53.6 million dogs. Let me double check that number, 107.2 divided by 2. Okay, good. So that's the number of dogs in the U.S. Now we can take that and we can go back and plug it into either one of these equations. You can plug it in here or here. Doesn't matter which one, to solve for the number of cats. I'm just going to plug it in the top one. Cats equals dogs, 53.6 plus 7.5. So 53.6 plus 7.5 is 61.1. So the number of cats, sorry about that, is 61.1 million. Number of dogs is 53.6 million. You always want to make sure what you have makes sense. Back in the original, it said that the number of cats exceeded the number of dogs. That means it was bigger than the number of dogs. So that is true. We have 7.5 million more cats here, and if we add these two numbers together, we get 114.7, which is what we're supposed to get. This next example is very similar. It says you are choosing between two long-distance plans. Plan A has a monthly fee of $20 with a 5 cents a minute fee. Plan B has a monthly cost of $5 with a 10 cents a minute fee. For what amount of minutes is the cost of the plan the same? So let's say that Plan A costs us $20 a month and then 5 cents per minute. So I'm going to use M to represent the number of minutes I talk on the phone. So notice, 20 doesn't have a variable with it. I'm just charged that one time, $20. Then I add 5 cents per minute. Plan B, I'm only charged $5 a month, but I'm charged 10 cents per minute. So I have to multiply the number of minutes I talk times 0.10 to figure out what I'm going to get charged. Now their question is, when will the plans cost the same? In other words, when will these two be equal to each other? So that's exactly what we do, is we take these two equations and set them equal to each other. Remember, if you have variables on different sides, you need to try to get them together. So I'm going to move the 0.05m over to this side. That gives me 20 equals 5 plus 0.05 times m. Subtract 5 from both sides, and I get 15 equals 0.05 times m. And then I can divide both sides by 0.05. And I get that when we'd have 300 minutes talked, the plans are equal. So if we go back and we think through this a little more, we can see that if we plan on talking less than 300 minutes, then Plan B would be the way to go. Because Plan B has a lower set cost. It's only $5 per month. So it doesn't matter to me that the number of minutes is higher. Excuse me, the cost per minute is higher, since I'm only going to be doing 300 minutes or less. On the other hand, if I'm going to be speaking more than 300 minutes, I would rather use Plan A. Even though it costs me a $20 a month fee, in the long run, the fact that they charge less per minute is going to save me money if I'm going to talk more than 300 minutes. Okay, one more example similar to these. It says the length of an NFL field is 200 feet more than its width. So we'll use L and W for length and width. So the length is equals 200 more than the width. So the width plus 200. It says if the perimeter is 1,040 feet, what are the dimensions of the field? Well, that field is rectangular, so we know 2L plus 2W is the perimeter. They tell us that's equal to 1040. So this one's a lot like, not the most recent problem, but the one right before that, where we were dealing with cats and dogs. Because we want to take these two equations and substitute to solve for L and W. So I'm going to replace that L with W plus 200. Bring my work over to the right side here and distribute. So 2 times W, 2 times 200. So that's 2W plus 400 plus 2W equals 1040. I can add 2W plus 2W and get 4W. Subtract 400 from both sides. And then divide both sides by 4. And 640 divided by 4 gives us 160. So our width is 160 feet. And again, you can go back and plug this in either one of the equations. I'm just going to choose the top one and get L equals 160 plus 200. So the length is 360 feet. So our length is 360. Our width is 160 for an American football field. Alright, almost finished. This is one other thing you need to know how to do, and that's not necessarily solve a problem, but just rewrite an equation so something else is what it's set equal to. For example, right here, right now we're set equal to P. It says 2L plus 2W equals P. But what we want is it to be W equals whatever that would be. So we need to get W by itself. So I'm going to subtract 2L from both sides and get 2W equals P minus 2L. I'm almost done because I just want to get W by itself, so I divide both sides by 2. Okay, now you can write this a couple different ways. You can write P minus 2L over 2, or you can actually go and divide both of those by 2, and you could write that as P over 2 minus L. Because if you do P divided by 2 and 2L divided by 2, that's what you would get. So there's a couple different ways you could write that, but both of those are correct. I want to look at one more like this. It's a little bit trickier. Right now I'm solved for A. A is what it's set equal to. But I want it to be solved for P. Well, if you notice, there's more than one P. So how do we get it by itself if there's more than one of them? The key is to make sure they're on the same side as each other, which these are, and then to factor them out. So if you notice, this piece and this piece both have a P. So I'm going to factor out that P. That leaves me a 1 plus RT. Don't forget that 1. You can't just make that disappear. So you pull the P out front, and now there's just one P, which is what you want. We want to get that one P by itself. So once you do that, you just divide by 1 plus RT, and you get P equals A over 1 plus RT. This is all coming from section 1.3 in our book. There's practice problems starting on page 103.